All right, thanks for coming, everybody. We'll begin with our technical talk here with Johnathan, and then move into the AGM, and then probably the real reason we're all here is for some social time at the Moose, right? Johnathan Kuttai graduated from the University of Saskatchewan with a BSc in Geophysics in 2010 and began his career in data acquisition, borehole surveying, EM, Northern Saskatchewan, winter. Really learning what's going on. Johnathan joined an instrumentation group writing software for signal processing, large-scale DC resistivity, and IP data. During his career, he gained experience processing and acquiring many kilometers of EM and potential field data worldwide in cold, hot environments, flat, mountainous, desert, jungle, and everything in between. In 2017, he joined SIMPEG Group to explore the geophysical inversion space, which led to an interest in doing a PhD. Currently with the UBC Group, researching avenues in geophysical inversion and machine learning, and works part-time doing inversion research with CompGeo. I will pass it on to you.
Whoa!
Well, thank you everybody for coming. Thanks BCGS for having me. And yeah, so today we're gonna show you some of the research that I've been up to. And yeah, it's an automated approach to incorporate structural information into the inversion using intersegmentation. Slide. There we go. Yeah, so as geophysicists, we hope to answer the geologist questions, mostly about structural depth information and what are the mineralized zones? Where do we draw? And to do that, we usually go out to somewhere that's hopefully geologically interesting. We acquire some data, we process that data, and then we produce geophysical inversions, or geophysical models using geophysical inversion. But these unconstrained inversions can, these models lack definition. The dips are quite ambiguous, and you get a little blurry image. It's not a very clean picture. So the motivation is can we improve these recovered models by incorporating structural information? And oftentimes, you guys probably all know, we don't have that prior information. So is there an automated way to incorporate that information or to interpret it? And we're going to discuss that going through an outline today of we're going to look at inversion with rotated gradients, and then segmentation for feature orientation. And then we look at segmentation guided regularization, and then looking at my most recent research in segmentation and ADMM, which is the optimization technique. So first, the inversion with rotated gradients. So geophysical inversion, we usually got this objective function where we're minimizing, we're using an objective function with a data misfit and a model norm or regularization. And we have that, we use our model vector, or that takes in our model vector, and then we have a beta for our trade-off parameter for our regularizations, how much we want to actually add for regularization. If we expand that a little further, our data misfit term is measuring how well we're fitting our data. We have a weighted matrix that has our uncertainties in our data. And then we have a forward model operator that acts on our model vector, and that compares it to our observed data. And then on the regularization side, we have usually a regularization operator and then our model vector compared to a reference model. So a common model norm or regularization that we use contains a smallness term and a smoothness term. And yeah, if we look at our smallness term, that's looking at comparing it how close we are to our reference model, whereas our smoothness term is looking at where our gradients are. So it's that smoothness term that we can modify, and we can input a new A tensor, tensor A, which encodes our orientations, our new principal axes of our orientations, and the elongations, our alphas along those principal axes. And we can define that for every model in the cell. So we can actually have regions where we can rotate and not rotate and kind of look at the structures, and we can define them in certain areas. So if we just take a look at that, we just do a simple pull dipole survey of a DC survey, n equals 16. And then with survey equipment nowadays, you can collect more than one dipole space. So we just do 25 to 250, get some decent information there. And we're just going to do that over a dipping conductive dike intrusion synthetic model. So it's just a conductor and a resistor. And if we carry out the L2 inversion, we get what we expected, just a blurry image and an ambiguous dip. Yeah, could be better, but we can use it to interpret. So if we start adding in this new smoothness term, we can, with that prior information, knowing that it's dipping 45 degrees to the west, we can rotate all our principal axes to, well, in this case, 135, so that we're dipping westerly, and then we accent along our major axes. So our new X prime, Z prime, so our rotated principal axes. And we actually now recover our pretty good model with a good estimate of the dip. And then this is just to show that we can actually just focus that. We can rotate just within the area of interest where we have our structure, and then we can just leave it normal everywhere else, and we should end up with the same result, which we still get that same good dip estimation. So that data fit using the rotated gradients, we actually fit the data in fewer iterations, almost half, and our models are simple. They're actually better models, and they're more accurate as well. But we don't always have that information. So how do we use what we have to interpret the structural information that it's trying to tell us? And that leads into segmentation for feature orientation. So we're going to start borrowing segmentation techniques from computer science or computer vision. And so to the overall arcing method here for the feature orientation is three main parts. We're going to do the segmentation itself, which provides the masks and defining the structures. And then we have mask processing. This is going to give like some order to the masks, dealing with overlapping masks. And then once we have that, we can determine our orientations and our elongations using principal component analysis, PCA. There are probably other techniques, but this is just the one that we chose because, yeah, it gives us a lot of useful information. We can use the explained variances to find our elongations and our outputs. So first, the segmentation provides two important pieces of information. It isolates the structural object, and then it gives us also a boundary region. So we don't always just have to rotate within the actual, we don't have to identify where the structure is exactly. We can get kind of like an idea of where the structure should be. And then we can tell the inversion to focus its orientations in that defined area. And we do that segmentation using transformer machine learning model called transformers. And these transformers are quite useful because they derive they provide a context derived from the whole image. So if you see here, we query a pixel on the neck and we get a heat map that tells us what actual other pixels are important to the segmentation. And we can represent this idea of context using the mathematical construct attention, which at its base uses three main matrices, which is a query, a key, and a value matrices. And these all encode the information of how one pixel correlates to every other pixel in the image for every pixel. And then with that, we can get a attention score. And that gives us what the pixels that we need to pay attention to when we do the segmentation. And then to improve that, to improve that performance, we want to do that lots of times. So we do multi-headed attention. And then that's what that allows the attention mechanism to attend to certain areas all at once. Each head can attend to certain areas. But there's one drawback with transformers, and that they're incredibly hard to train. They need a lot of data, and making a lot of geophysical inversion models to train that, it's kind of hard. So what's often done in that area is that you take a pre-trained model, and then you can fine tune after that. So here we look at Meta's segment anything model, SAM, which is all the heavy lifting is done on the encoder side. So it is based off of more of a vision transformer, which is all on the encoder side, and then the decoder is just kind of a simple mask generator. And we've actually found that right out of the box, even training on ice cream trucks, you can determine structures in the geophysical inversion. And so now that we have those masks, we want to do some processing. So the easiest one is some hierarchical ordering. So we do like largest mass to the smallest, or smallest mass to the largest. Or if you have overlapping mass, you can kind of trim them out. And that's kind of on the second part here. So once we have the mass, we can do kind of an intersection of unions algorithm or equation, and we can kind of assign how each mass correlates to each other. And then we can kind of get this image here. So this one is we're taking like a early iteration of the geophysical inversion, and then we just run the segmentation. And with our eyes, it'd be kind of hard to pull out 3 different segments, but the segmentation actually does catch that. And it gives us a kind of a range of what what the inversion is telling us of the structures within. And that, we have overlapping masks, so that we could just, meld them all together or not. And since we have the mass and we have them outlined, now we can use PCA to get our elongations, which are our alphas, and our orientations, which is our principal axes, and where we're going to rotate them and point them down. And then from that, we use the bounding boxes to actually assign those alphas and those orientations. If we focus on just where the segment is, we're not giving the inversion a lot of room to play. So at least with using the bounding boxes, we allow the inversion. Okay, we want things in this direction, but look at this whole area and push it that way. So now we have all the ingredients to incorporate structure, and we know how to incorporate that structure using the rotated gradients. So let's put them together. And we'll look at the segmentation guided regularization. So the workflow here starts with the data, of course, and then we run the geophysical inversion for several iterations, and then we perform the segmentation and the mass processing. But then we have 2 options. We can update the regularization and estimate the new beta and continue the inversion, or we can update the regularization and then restart from the half space. So we kind of figured out the prior. Now we just want to run a new inversion. So we start again. We look at our dipping conductor inside the resistive background, and we run the L2 inversion, and we get our result. It's blurry and ambiguous dip again. So now we do our segmentation, mass processing on we kind of have to set like a schedule for the segmentation. We don't want to do it too late so that the inversions already fit the data and everything's there. So we want to set a schedule to do it early on, and then however many iterations you might want to add it in again just to see if the structure is changing. But here we're just going to iterate for about 4 iterations, and then update the regularization, estimate new beta, and then continue. And with that, we see that, oh, well, we're getting a better estimate on the dip. Still a little blurry, not perfect, but it's not nearly as ambiguous. Now, if we update the regularization and restart from the half space, we get quite a good result. We get a much less ambiguous dip and a pretty good estimation on it. And then again, we're not really fitting the data any earlier or any quicker, but a few iterations. But what we are seeing still is that we're ending up with simpler models. The regularization is much less when we actually incorporate the structure. So those synthetics do look promising, but how does it do with real data? So we're going to look at a field example here, the McDermott deposit. This is a gold deposit in Ontario, steeply dipping sulfide body embedded in metasedimentary rocks, and then that's overlain by some glacial sediments that are quite conductive. However, this data set is a little old, so it's only n equals 1 to 4, so not a lot of data. A equals 40. It's a dipole-dipole configuration. DC and IP are both collected at the same time, so we've got 2 data sets to try it on. So if we look at the resistivity inversion, the normal L2 is really focusing on that conductive layer at surface. It's really sucking everything up. But if we segment early enough, we can actually start to preserve that depth structure. So if we do the first line through the workflow, where we go
estimate new beta and update the regularization, yeah, we can preserve that structure. We get kind of the boundary between the two focus elements at the bottom. And then, yeah, if we go the full way and restart, updating the regularization and restart from a homogeneous half space, yeah, we still get the same result. It's a little bit different, maybe kind of pulls down the conductive layer a little bit more, but yeah, ultimately we've preserved some structure at depth. But if we go to the chargeability inversion, I just want to focus here that the mineralization zone actually is broken into two. It's kind of symmetric where it's got a higher concentration zone and then a higher concentration zone. And when we run our algorithm through this, the target is a little symmetric. So we're not getting any elongations along the principal axes. So there's nothing in the inversion telling it to kind of to accent along any of them. So to combat that, if we use the conductivity model's orientation information that we got from the DC, the dipping structure is starting to get a little bit resolved. We're starting to actually see that whole zone is dipping. We're not kind of focusing on one side, the concentration or the high concentration. So then let's look at another field example, MacArthur River here. This is going to be looking at some MT data from the Athabasca Basin. And if you're not familiar with the Athabasca Basin, it's a sandstone overlaying some basement rocks, and this unconformity is where the uranium is hosted. So these faults occur along the unconformity and allows fluid to come up, do some alteration. It's usually a graphitic conductor, or graphite is kind of deposited there, and then hopefully near the top, like you can have an ingress or a digress, so you can have in the sandstone the alteration and the uranium form there, or it can be down in the basement, depending on which way the fluids are flowing. You could have both if over time they kind of go. But it's these graphitic conductors that are the target that are kind of indicating where the uranium could be. And for this example, we're going to look at one line of data here, the one in the north, because at the time these were labeled the P1 and P2 conductors, and this line covers both of them. So here we first look at just doing a combined TE-TM mode L2 inversion. And yeah, the results actually aren't too bad right out of the box. We kind of can infer that there's two conductors there, and that yeah, actually where the data came from, there was a report with a few drill holes, and we can see that the L2 inversion is actually doing pretty well. We're starting in a high resistive zone at the top, and then going into a lower resistivity near the unconformity and into the base. So already the L2 is, it's doing pretty good. It matches the drill logs for how deep they have. So if we go along our first route, and again, just update the regularization, estimate new beta, we can actually start to decipher two distinct conductors. The P1, maybe we're not getting quite a good estimate of dip, but we're at least separating and getting two conductors. And then if we go the last route, where we go and update the regularization and start from homogeneous half space, we actually get a really good estimate of it. We get a dip out of the P2 conductor. And again, if we look at where the drill logs are, we're still seeing that, matching the drill logs. Whereas the P1 conductor, we didn't actually get any elongations. This is kind of one of those, again, another one of those conductors where it's symmetric and we can't get anything from the PCA. But this is not really a shortcoming of the technique. Talking with some of the geophysicists that work in the Athabasca Basin, Cameco, some of these faults can occur in packages. So this could be 10 faults all along. So what this more likely is it's a lack of resolution in the survey itself. Whereas the P2 conductor, if we look at the seismic data that was collected over here, we actually have that shallow dipping P2 conductor. And there's a group of maybe 2 or 3 conductors here, whereas the other one is probably a large group. And yeah, looking at the literature further, that P1 conductor doesn't exist anymore. It's like CA, C1, C2. There's quite a bit in there. So it's mostly a lack of resolution that's kind of hindering the technique there. And yeah, so now I'm looking at time domain in that area to see if that can help decipher or discriminate those conductors in the P1 zone there. And yeah, so again, we're not really fitting the data any quicker, but we're still fitting the data. but we are still ending up with simpler models, way less regularization to put in. So that's one way that I've looked at looking at segmentation. And is there other ways that we can incorporate it into the inversion? Is there, like, right now it's kind of sitting on top of the inversion. It's like kind of acting from outside and acting on the inversion. So is there a way that we can make it more mathematically like cohesive? And there is. So that's segmentation in ADMM, which is alternating direction method of multipliers. And it's a way to solve some optimization problems. So here, I'm going to add segmentation to the objective function itself. So now we've got this little bit larger objective function where we have our data misfit term. We can now add a kind of a PDE form of our segmentation that will act on the model vector, and then a new auxiliary called Z. And then we have a regularization for that. And then we have a coupling term that kind of bridges the gap between the model space and the auxiliary space. And we want to solve that such that our model vector is equal to the auxiliary space, but the auxiliary space has classes, so that we want to have the segmented class. So we want the model vector to match the segmentation, what we're saying here. And yeah, so M is our model, Z is our auxiliary model, alpha is our trade-off for the segmentation terms, beta is for the regularization of the segmentation, and then gamma is our trade-off for our coupling term. So then to state the full Lagrangian, again, we have our data misfit term that's using a forward operator on our model to compare to the data. And then we have our segmentation term that's looking how close the model is to each class. And then we have the regularization for that auxiliary space, and then the coupling term, which is kind of like a smallness term that couples the two spaces together. And then our NC is the number of classes. So this is something that we initiate in the beginning. And then that's how our segmentation is built off of. And then some more coupling terms. And yeah, so just to note that these classes are all user defined. This is not an automated thing right now. Oh yeah, then sorry. But then what's also included here is this U, and this U is another term that kind of couples the errors between the two spaces. So according to Boyd, in his 2010 paper, the ADMM solves this equation iteratively, alternating between the two spaces. So it looks like, oh, well, maybe I've made a lot more work for myself now. Now I'm solving two steps. Well, there's three steps here, but I'm solving two like objective functions in a sense. But the cool thing is that step two, with some mathematical gymnastics, we can actually represent that as a proximal operator, and that is effectively almost just like doing just executing an analytical function. So you don't have to do a whole bunch of solving. So all the work kind of is done in step two. Or step one, and then step two is just the segmentation itself, and then step three is just the running errors between the two spaces. So this is just kind of out of the box. Let's go back to our dipping conductor, and we see the L2 is still doing its L2 thing. And then when we look at the ADMM side, it looks like the segmentations are actually pretty similar to what we get with sparse inversions through what I would have been doing in SimPeg. And then on the far right here, I've ran these all the way to about 30 iterations because that's how long it took for just the regular L1 and the other sparse norms. Because you fit the L2 and then you iterate, reweight, and then keep going. Whereas with the ADMM, we actually arrive at these results in a fraction of the time, like several iterations as opposed to 30. And yeah, then that regularization term in the segmentation, as you dial that in, you can see you can tighten up. You start here, and you can it gives you a knob to turn to get you how sparse you want your result. And then the other cool thing is, since that auxiliary space is a number of model parameters by classes, you actually solve for the portions. of what class, how much that class will contribute. And then in that sense, you can kind of get kind of like an idea of some uncertainty along your edges. And then this one was for Thibault, but he's not here. He wanted to see this model done. But yeah, so I went to like, let's try this in a little more complex simulation. And then here I started playing with some adaptive Gaussians to kind of estimate how many classes there should be. And yeah, like so far it produces, sorry, uh-oh, how do I go back? Not right there. Yeah, you can see here that our auxiliary space segmenting out, it's not segmenting out all 4 classes, but we're getting the surface. We're actually getting the intrusive here. Depth is kind of a problem, but you know, that's actually kind of giving us a dip estimate. And then we're getting that higher resistive zone here, that layer, and a little bit of the faulting. And then the geophysical model, yeah, come from the geophysical space. So yeah, looking promising. A little bit of work, but now it's all in one mathematical step in a sense. Nothing kind of acting outside. So this brings me back to the motivation. Can we improve the recovered model by incorporating the structural information? And without that information, is there an automated way to look for, or to interpret that structural information? And yeah, the answer is yeah, a structurally informed regularizer gives us simpler models and better dip estimates. And then image segmentation allows us to automate that by identifying the structure, kind of what's happening early on in the inversion and enforcing what the inversion is seeing right in the early steps. And that's all.
So if you did have dip information, where would you insert that information in the?
Right off the bat, it'd be kind of just like going that second row. If we had already that information, like you wouldn't have to do the segmentation technically. Or we could just plug it right in and just do the last or the second step to the flow.
But what if you have a single point, right, and then the rest you don't know?
Oh, okay. Well,
Yeah.
then yeah, I'd plug in what you do know and then just carry on, just to see if that is enforced. I have found some cases where if you can put the wrong dip, yeah, you're going to iterate out to 10. It's going to try and correct it, but the data still is kind of going what's happening there. If the data doesn't support it, it doesn't quite want to follow it. Just like even that example with the MT, when I had that vertical dipping, at that point I didn't know what the dip was, and I was getting out like some other dips, and then when I was enforcing it, it just didn't really want to move. It was moving, but not so much. But it wasn't until I actually, had the information that if I had the right information that the data supported, it's faster.
So John, you've figured out a way to override the what do you want it to be
Yeah.
problem. So the geologist got a couple holes and you think, so it's gotta be dipping this way, and this is the structure.
Yeah.
You can run this and really convince them and show them you're dead wrong. It's
Yeah.
gotta go the other way.
You could, yeah.
That's cool.
The others. And also like you can see it in like the model regularization too. So as I was showing, like we're always ending up that simpler model, and say you do put in the information that they think it is, and you get a model out that supports them, you can look at these other like the regularization and see that, oh well, this is not actually what, like this is not the typical behavior of the method. So you can get a good guess out of it that way as well.
So John, hey, great talk, Kyle here. Just thinking about some of the work that we're doing with computational geosciences, Jeff and the gang here, and we do what we call geologically constrained inversions.
Yeah.
Just for one example, we like to put in the Athabasca Basin unconformity for your example on MacArthur, where we'd expect to see a different conductivity contrast in the sandstone compared to the basement.
Yeah.
So how would you go about segmenting a problem like that where the unconformity is relatively well known?
Yeah, well, this one, actually that example is kind of interesting because I'm privy, right? I know that there's that unconformity there, But as you can see in that model, it looks like it's pulling down that sandstone. But apparently that's not always the case, is it in that area, the sand or the basement can be more, it can be as resistive. So it would depend on where you are, and if there is a big enough contrast, it should segment out. Like you'll get like a weird segment where the conductors will just be holes, and then if there is a big enough contrast, and I think you would have to enforce the unconformity and weight it at the interface there. And if you had that distinction, it would segment out. I would. As long as you have the like some sort of contrast there, the segmentation would catch it.
Yeah, actually going back to that MacArthur example, what natural source data were you inverting again? Was it impedances or?
That was impedance, yeah.
Okay.
Yeah, that was just impedance, yeah.
Okay, yeah, because I was curious what would happen if you tried to use something that doesn't have a direct sensitivity to the structure. So whereas you've got something like ZTEM, you have some data sets that have not direct sensitivity, but they're sensitive to certain things. Like, I'm just curious how it might behave.
You probably aren't going to get as good a dip estimate, because that's kind of what it's showing here is if the method, or if the acquisition is not resolving the actual target, it's going to look symmetric and it's not going to be anything. So I'm guessing, yeah, if the airborne ZTEM isn't able to get a dip or any sort of like isolating the conductor, you're probably not going to get an estimate out of it. So it comes down to battling with the actual methods for acquiring the data.
You had something that was dipping within reason, like something in the data would tell you that that's a
Yeah, if
different
you were
signature
seeing it
than
in the
something-
data, it would segment it, and
Yeah,
it
yeah.
would give you that information. But as I've been seeing here and what I've heard from in the basin, it's mostly the airborne is there to see the corridors, and then they go into the ground and do the discrimination that way.
What's your intuition? Why, like, restarting from zero, like from the L2 versus constantly updating? Why one perform better than the other?
I think it's like a fight between it. When you start from the homogeneous half space, it's just like a clean plate.
Yeah.
And it allows it so much more. Whereas when you update it in the middle of the inversion,
It reinforces itself.
yeah, it's just kind of battling, and it doesn't. Well, first it's got to overcome what is already there, and then it starts going. So yeah, that's the one thing I haven't fully tried. Like just kind of letting it run for say 50 more iterations after that. Maybe it would come out. I've tried going like 10 iterations more, and it still seems to fight. Like you can see in.
It's marginal.
Yeah. Yeah, like it kind of does this. This is like the best case scenario is if you run it enough and then you get an idea, but it doesn't quite clear up. Maybe after X amount more iterations, you'll end up in this same as restarting, but by that point, you may as well restart it anyways and done it. End of the solution.
So is there some way that you can set, I guess, how forgiving it is to update the rotated gradients? Because that's sort of what I'm thinking. It sounds like you're running it to figure out what the gradients should be.
Yeah.
And you're like, the model I'm recovering is, I know I'm not satisfied with it.
Yeah.
But I'm really confident that I got good gradients from this. And then I started with that.
Yeah.
So then do they sort of change slowly? They just need enough time, or can they change for an individual cell? Can the rotated gradient that you're applying change quite rapidly when you're updating?
When I set the schedule to go, like say iterate or segment on the 4th iteration, 8th iteration, I didn't see too much, but it does change. It'll change by a few degrees, but not a lot.
So in the first few iterations, it really does most of the work.
Yeah.
Then you're like, I got my gradients, but I'm not married to any particular structure. Let's restart it. And then that's like
that seems to be the best route. Yeah.
Is there anything to studies on how robust this is to noisy data?
Not yet, but yeah, I'm not going to be very robust. If you've got artifacts, the segment's going to find that and it's going to segment it. The only thing I have to combat against that is that's when we can start playing with like the rules in the hierarchy, or like the mass processing, where like I've had some DC, you can see there's always sensitivity near the electrodes. So you got little blobs and whatnot. So if you segment that out, it's usually a couple pixels, so you can kind of discard those masks. But I would say that would probably be the same thing that happen if you have bad data in there, noisy data, you're gonna get these little isolated masks, and maybe you can throw them out, but it's probably better to just get a handle on the on the noise and then carry it out.
So John, can you run this methodology on any type of data? And which type of data do you think is best suited for this methodology? And then also like what geology?
I don't think it's necessarily the method, but the acquisition method is the most important one. It's you gotta be using it can work on any method. I've used it now for IP, BC, MT, and time domain EM. I have been playing around with potential fields, but that was on the other the new stuff. But yeah, you can apply to anything. It's just as long as the acquisition type can resolve what you're looking at, you can pull that information. It's not that it's gonna make up information. It's gotta be there in a sense. So yeah, if you've got big blob that's over something that's actually something small, yeah, it's not gonna work there. But if you do have a method that will, like a plate or something, and you know it is, yeah, it'll enforce it.
Well, possibly incorporating structural information from geologic maps.
That was
That
awesome.
usually you got some sort of map to start with.
Yeah, and we actually have played around with a few scenarios where, yeah, they've known that dip should generally be in that direction, but that just speeds things up is essentially what it does, because then we can program it right into that like that initial regularizer, be like, okay, you know it's supposed to be this way, and then you can kind of go from there, and you can run the segmentation, and if it disagrees, then then we gotta step in another direction.
Thibault's not here. I'll ask a question for Thibault. How does it, like, what's the difference between ADMM and the Gaussian mixture, like the way it works?
This is actually one of the question that he did that Cobalt asked. It's very similar. What their question was, which one's better?
Okay.
So I said mine, of course, because it solves it in a lot. Like you actually don't spend a whole lot of time in the space. You get to the solution quite quickly.
Okay.
So I think the difference here is that to me it seems it's a little bit more robust. You can start it right off the bat. Well, the second part of the research there, you can start it off right off the bat.
Without L2.
Yeah, you just put in your segmentation and run the inversion. Whereas with PGI, you kind of want to give it some time to generate some kind of structures in there and then kind of kick it in. So it's not a lot different. It's kind of conducive to each other. Yeah. So like that's the other thing that Thibault and I were talking about is that, you know, from this auxiliary space, now we have the proportions and we can now plug that into the PGI. And that will be something I try next.
Proportions in terms of the size of the population or like the
Yeah.
standard deviation of the
Yeah.
population.
It would be or what each class contributes. So so for each petrophysical measurement that you put in there, we can actually solve for its contribution to that GMM, the EGI side. Whereas right now it's you kind of initialize it and then add in.
So thinking about your colleague, John Weiss, and he gave a really good talk on different types of magnetization of BCGS. And so what could that look like if you combine this method with some of the things that he's working on? It's a pretty broad question, but
Yeah.
I just wonder how the segmentation could work for remnant magnetization.
Yeah. It's a good question. I don't actually know. I think I have an answer to that.
I hear you're bidding for orientation, but
Yeah.
you're bidding for populations, I guess.
Is in it for that. Yeah, there is probably a segment or a way to incorporate that. So instead of the classes, you could just have what's magnet or what's remnant and what's out. Yeah, so actually that's a good idea. That might be something to talk to John about it.
Are you running the SAM kind of any other part of GPU or should it?
The SAM is on GPU. Everything else is unfortunately. Yeah. But that actually in the second part, I'm not using SAM anymore. I'm using the PDE form of the segmentation. But I've been digging around in that SAM model now a little bit, and I think I can actually make it so that that could be my segmentation term. So then I'll have at least the first part of a GPU into the objective, using the SAM model. But yeah, I just got to figure out how to get the gradients out of that model first. I'm close.
Anyone online wanna ask a question? Unmute yourself. We're gonna hear you. Thibaut, you're here.
Yeah, no, thank you, John, for the slide. I saw everything. Thank you for
I use that model. I know you were concerned that I didn't, so.
Well, you teased me with it last time, but didn't use it
Yeah.
in the end.
No, that was a good point. And actually, yeah, I ran it with that model, and it was pretty fun result to get. Pretty promising. So thanks for that, Tilo.
How did Tebow get his own little special model? I get it.
He built this one, so that's why.
There's no other questions, and thank you very much.